Good morning. Today we can go a little deep into the properties of enthalpy. So in the last class we have learned the different thermodynamic potentials like internal energy, the Helmholtz function, the enthalpy and the Gibbs function, etc. And we can take these potentials one by one. The internal energy we have already learned in the second module, first law of thermodynamics in that module. And today we can go a little deep into the properties of enthalpy. Enthalpy is represented by the letter H. So in the earlier chapter, in the first law of thermodynamics, in that session, many times we have used U plus PV like term, U plus du plus PV like term, and U plus PV like term we used. So the enthalpy is actually given by this equation, that is UH is equal to U plus PV. Properties, the peculiarity of this equation or this potential, we can consider a process in which it is an adiabatic process, because this process is under adiabatic conditions and we are taking some gas in an adiabatic chamber and we are using pistons that also adiabatic and also some porous wall that also adiabatic. So we can draw that picture. So what we are doing is actually we are controlling the pressure. There is two chambers actually, either both sides of this porous wall. There will be a porous wall, and both sides there will be a small container or small sections will be there. So we can transform. At first we are taking the gas in one chamber, and the next one by controlling the pressure, we are moving the piston. So the next chamber will expand because there is also some piston and it will go backward, and the gas from one container can be moved through this porous wall easily to the other side. So we can draw that picture. That is, this is an adiabatic, this is adiabatic container. Actually the walls are adiabatic walls. It will not allow the heat to flow out, or it will not allow any heat to come inside. So we have two pistons here. That also adiabatic one. This is also adiabatic piston. And there is a porous wall. This force will allow the gas to move on the other side. This is also adiabatic wall. So initially attaching to this wall, the second piston is there. This is also adiabatic piston. The volume here initially VR. So we are filling. So there is gas here in the first chamber. There is gas here. So what we are doing is, by controlling the pressure, we are exerting some pressure to this piston, and this pressure is more than the pressure exerted on this piston, the second chamber piston. So we are by controlling the pressure, we are moving both the pistons simultaneously, but the pressure on this piston is more and the pressure on this piston is less than this piston. So the pressure at this chamber is more than this side. So the pressure is maintaining at a constant. So when we are giving the pressure is here is Pi. So while we are giving the pressure, chamber will pass through this pores. Then this piston expand and it will contain or it will enclose in this chamber here. It will move backward. So the second picture, after all the gas is moved to the second chamber, the next picture also we can draw. This is the container, the same thing we are drawing. So here we have this porous wall here. This is again adiabatic. This is the same thing we are drawing. So what is the final condition here? Finally, the piston, piston of the second chamber is here. And the piston, after all the gas is moved to the other side, then this piston will come close to the porous wall. So now the pressure, the volume here is some Vf and the pressure here is some Pf. So Pa is greater than Pf, we are giving in such a way. So this is this one is Pi Vn and this is Pf Vf. So we are maintaining the pressure, and it is actually this type of process is known as throttling process. Throttling process, or it is similar to Joule-Thomson expansion. Or it is also known as porous plug experiment. So this throttling process or these processes like that, a gas or a liquid at high pressure can be converted into a low pressure one. Here also we are doing the pressure on this side is high and the pressure on the other side is low. So these process we are controlling the pressure, and we can convert the gas or liquid from a high pressure area to a low pressure area. So converting the gas from a high pressure state to a low pressure state. This is also known as porous plug experiment. So we can use the enthalpy property here. Actually, in the throttling process, the enthalpy is a constant. The before process and after process, the enthalpy will be a constant. That is one of the peculiarity of this type of processes. We will obtain that equation. In order to obtain that condition, we can solve, or we can derive that equation, or we can solve that property. Property 1 of the enthalpy, that is the first property. That is the property is not changing, or the enthalpy is not changing before and after the porous plug experiment or the throttling process. So a throttling process, it is actually an internal mechanical irreversible process. Internal mechanical irreversible process, because while passing through the pores of this porous wall, the gas will exert some friction. There will be some friction between the gas molecule or the atoms and the walls of the pores. So there may be some dissipation of energy. So this is actually an example of internal mechanical irreversible process. So throttling process is an example for internal mechanical irreversible process. So in between these two states, that is VIPI state and VFPF states, in between a state is not in equilibrium because there is a dissipation of energy. So that is a non-equilibrium state. So we cannot write the equation of state for such processes. So in between we are not considering what is going on in between. So these two states, the initial state and the final state, are in equilibrium. So you can use the potential equation, thermodynamic potential. We can define, we can use the thermodynamic potentials to represent the states of the system, and we can use equation of state to represent the system. At PIVA, this condition and this final state. In between states are non-equilibrium states. So from first law you can write, what is the first law actually? The change in internal energy UF minus UI is equal to W plus T. This W is actually diagonal work. Since this process is an adiabatic process, we can write Q is equal to 0. So we can write UF minus UI equal to W. So what is actually W here? There are two volume change here. One is the change in volume in this chamber and the other is change in volume in this chamber. So total work we can represent by minus integral state 1 to 2 PB. So here we can split this integral into 2, which is equal to minus of integral. So pressure in this chamber is constant Pi, pressure in this chamber is also a constant Pf. So the first chamber, what is the volume? The initial volume is Vi, the final volume is 0. Initial volume is Vi, then final volume is 0. Then Pi dV. Then the second one, minus already we have taken outside, plus integral. The initial volume of the second chamber is 0, the final volume is Vi, the pressure is Pf d. So we can just erase this section. So what is this one? This is equal to minus integral, minus Pi, then V from Vi to 0 plus Pf, the second integral is Pf is a constant, then V from 0 to Vf. So which is equal to minus of Pi into 0, V equal to 0 first, then minus Pi into Vi, then plus Pf into Vf, plus Pf into Vf. Which is equal to minus of Pf Vf minus Pf Vf. So this is actually W. So we can write H is equal to, or UF minus UI is equal to, UF minus UI is actually W that we have already written, equal to W, which is equal to minus Pf Vf minus Pi V. Then you can combine these two terms. Vf terms can be taken in one side and the Pi terms on the other side. Then Uf plus Pf Vf equal to, this is minus minus plus, then minus Ui this side, Ui plus Pi V. What is U plus PV? U plus PV is nothing but the enthalpy X. So we can write HF is equal to HR. So you can see that in a throttling process, there is no change in enthalpy. The enthalpy in the initial state is same as the enthalpy in the final state. So even though pressure, volume, etc. are changing, internal energy also changing, there is no change in the enthalpy of the system, and enthalpy can be written as U plus PV. So in a throttling process, there is no change in enthalpy. That is the first property. That is, in a throttling process, there is no change in enthalpy, or the enthalpy remains constant in a throttling process. This is the first property, that is, this is the property 1. So, this is the first property of enthalpy, that is, in a throttling process, there is no change in enthalpy. The enthalpy remains constant during a throttling process. So, there are 3 more properties for enthalpy. Now we are not representing any temperature here, but during this process the temperature is also decreasing. So finally we will get a very cool one. So we can stop the first property, the first property here we can stop today. So the next properties we will take in the next class. Thank you.